Hi, in today's lectures, we are going to discuss some interesting concepts in solid mechanics, namely thermal stress, stress concentration, and residual stress. To start, let us consider two scenarios for a uniform bar on the screen, which has an horizontal length of L and is supported by a fixed support at one end. Suppose in the first scenario on the left side, we will increase the temperatures, and in the second scenario on the right side, we will decrease the temperatures within the body of the bar. The following is what will happen. As you can see, the bar elongates in the first scenario and contracts in the second scenario. It has been found from the experiments that the amount of elongation or contraction is linear related to the temperature change, and can be determined using the following equation. In this equation, delta T is the thermal elongation or contraction. T1 and T2 are the temperatures within the body of the bar before and after the temperature change. Finally, alpha is a property of the materials which is referred to as the linear coefficient of thermal expansion. As it measures strain per degree of temperatures, its unit can be 1 over F in the US customary system and 1 over C or 1 over K in the SI system. Typical values of alpha for some materials can be found from the tables on the inside back cover of the textbook. Specifically, here is the table for SI units, where in addition to the coefficient of thermal expansion, you can also find the parameters we studied in the previous lectures, such as modulus of elasticity, modulus of rigidity, yield strength, etc. Here is the same table for the US customary units. Now, to understand the concept of thermal stress, let us use the same example as before, but this time adding a fixed support at the free end. Then the following is what will happen with each scenario. Since the bar is not free to expand or contract like before, there will be stress inside the bar due to the change in temperatures. Specifically, compressive stress will develop inside the bar when the temperatures is increased, and tensile stress will develop inside the bar when the temperatures is decreased. Since these stress are caused by the increase or decrease in the temperatures, they are called thermal stress. Let us see how to find them, considering the first scenario, for example. As you can see, this is a statically indeterminate problem, which cannot be solved by a solo use of equilibrium equations. So let us use one of the methods that we learned in the last lectures to solve this problem. Let's say we use the force method. The idea is we will first imagine the support does not exist at one end that allows the bar to expand freely. Once we find the elongation, we will reapply the supports and its reaction to that imaginary free end to suppress the elongation. That said, here is the elongation of the bar if we pretend to remove the support at B. From a previous slide, we already know how to determine this elongation. Now, let us not pretend anymore and reapply the support at B with its reactions. Please note that what we are doing here with the force method are all imaginary. As point B is fixed in reality, the sum of imaginary displacement of point B caused by the temperature change, and the reactive force Fb should be equal to 0. That means we know the imaginary displacement of point B caused by the reactive force Fb. As we learned from previous lectures, such displacement allows us to find the average normal strain within the bar, which in turn from stress-strain relationship allow us to find the average normal stress caused by the force Fb. That normal stress is nothing but the thermal stress that we mentioned earlier. So to summarize, if there is a change in the temperatures of a solid body and it is not free to expand or contract, there will be thermal stress being produced within the body. As thermal stress are unwanted and may cause failure of a member, we have to consider them in the design of structures, especially though have a significant length. As you can see, railroad is an example of extremely long structures where we have to consider thermal expansion and stress. For that, expansion joint is commonly used. Its idea can be illustrated on the screen. Let's say this is the appearance of a joint when the temperature is low. On the days when the temperature increases, the joint will look like the following. As you can see, the continuity of the track is maintained with such design of the expansion joints. Now let us study something called stress concentration, which refers to the increased level of stress at certain area or location in a solid body. If you remember when we studied Saint-Venant's principle, we saw it already where the stress near the point of application of concentrated load is very high. The thing we would like to discuss in this lecture is the stress concentration also occurs at the location of sudden change in the geometry or material of a member. To be specific, let us consider the bar on the screen, which is subjected to an axial tension load. To visualize the stress concentration, let me introduce to you a technique that engineers usually use, which is called the force lines methods. It is based on the similarities between the flow of forces and the flow of water. For example, let us look at the free body diagram of the bar in equilibrium shown on the screen. Since the bar is in equilibrium, we know the force on the left is equal to the force on the right. If we think of this as water flowing in the pipe, then the amount of water coming in on the left side should be equal to the amount of water coming out on the right side. By drawing the trail of multiple droplets of water when they flow, we will be able to figure out the area of stress concentration in the bar. So let us see how it works. To explain, the red lines that we are seeing are the trail of the water droplets, the red dots that we saw in the animation. They are called force lines in solid mechanics. Since we know the stress is the amount of force exerted per unit area, the location where the force lines are dense or very close to each other should indicate stress concentration. For example, let us visualize the stress distribution for these two segments of the bar. As you can see, we have maximum local stress at some points on the surface of the two segments. Since the materials tend to fail at this location, in engineering design, we have to determine the maximum stress. In engineering practice, the maximum stress is found by multiplying the average stress with the so-called stress concentration factors, K. For convenience, this factor is reported in the graphical forms and can be found from the design handbooks. For example, here are the two graphs to find the stress concentration factors for two design scenarios. You can refer to the textbook to see how this graph are used. Now let us discuss the importance of stress concentration in the design of brittle material. For that, consider the bar on the screen, which is made of a brittle material. Suppose for some reason a small crack is introduced to the bar. As you can see, the crack leads to stress concentration at the tip of it. If the stress at this location is smaller than the strength of the materials, the bar is working fine. However, suppose we increase the load to the bar to a certain point, we will see the following. As you can see, when the crack grows, more force lines are disrupted, leading to more stress concentration. As a result, the cracks propagates very quickly over the cross-section, resulting in a sudden failure. So now the question is, what can we do when we see a crack on a bar of brittle material like this? Considering stress distribution, one of the solutions that engineers came up with was to drill a hole at the tip of the crack. As you can see, the hole moved the force lines further away from the cracks that reduce the stress concentration. To finish our discussion of this topic, stress concentration is often not an issue with the members made of ductile materials. The reason is there can be a redistribution of stress to the surrounding materials due to yielding if a point within the body is subjected to stress concentration. For example, if the same cracks as before is introduced into a bar of ductile material shown on the screen. Here is what will happen if we increase the load. We see that the yielding regions indicated by the yellow colors expand when the load is increased. Now we will discuss the last topic of today's lectures, residual stress. For that, let us use an example we studied before in which we have an uniform bar made of a ductile material. The bar is fixed at two ends and is also subjected to an axial load at collar C. However, suppose this time we increase the load to the point where there will be some permanent deformation in segment AC of the bar. Then this is what will happen when we remove the load. As you can see, due to the plastic permanent deformation of segment AC, the bar does not go back to its original shape. Because the permanent length of the bar is now longer than the original length, there can be compressive stress remaining in the bar. As such stress remains in the bar when its original cause, the external load P, has been removed, it is called residual stress. In summary, at the end of these lectures, I hope you have a clear understanding of thermal stress, stress concentration, and residual stress. Thank you and see you in the next lectures.